Greeting of the day. I am Rajkumar Parashari and I love doing physics. Today I am here with Z Advanced 2020 Physics Solutions of question number 1 and question number 2. My purpose is not the justifications of answers provided by NTA, but to share more insight, more depth, and if possible, the newer perspective. Be till the end of the video for the maximum benefit and subscribe my channel to get notifications in time. Friends, let us discuss question number 1. According to the first question, a football of radius r is capped over a hole of radius small r, and this hole has been made on a plank which is capped horizontally. So over here is a plank somewhere within this plank there is a hole of radius small r and a football of radius capital R is capped over this hole. So here is a football of radius capital R and this football is capped over this hole. If point P happens to be the point of contact of the football, then this point P should be touching this point C. Now let's read further. One end of the plank is now lifted so that it's get tilted, making an angle theta from the horizontal position as shown in this following figure. So the one end of the plank is lifted, keeping the other end fixed. If we see the whole figure, if we see the whole picture from the side, then this is how it should look like. Let's assume this side to be x, y in this diagram. This point is x and this point should be y. Let's read further. What we are supposed to do? We are supposed to find maximum value of theta so that football does not starts rolling down the plank. So we are supposed to find maximum value of theta for which football does not starts rolling down. Is that right? So that value of theta for which football stays within this hole, it does not roll down. Is that right? We are supposed to find that particular condition. So what solution has been provided is, the argument is, if you look at this figure, the weight of the football is W. This passes through the base of this hole, and that is why this football is in the stable condition and it should not be able to roll over this plank. Is that right? And if we tilt this plank further, so this is how the figure now should look like in this diagram. If you see these two things carefully, in the second diagram, the plank XY has been tilted further compared to its previous case. Now the weight mg happens to pass through the edge of this base. Now because this weight, the weight happens to just passing to the edge of this base, about to leave this base, and hence this football is about to roll down. This is what I am telling you, and we'll discuss in a short while. So anyway, let's continue with the argument. This angle is theta and this football is about to roll down. So this is theta, this angle got to be 90 minus theta, and hence this angle is also 90 minus theta. This angle should be theta. So in triangle COB, sin theta is equals to CB by OB, and this is equals to small r by capital R. So this is the condition. As long as this condition is followed, as long as theta is less than sin inverse r by r, this football will not roll over this plank xy. But as I told you, I differ with this argument. I mean, though this answer matches with one of the option given in the problem, but I do differ from this particular argument. You see, I mean, when the football rolls over a plane, this is a football, or this is a sphere, and this is the plane. I mean, then you notice that the rolling condition requires that the line joining the point of contact till the center PO must be perpendicular to the surface on which it is rolling. Is that right? And this is always satisfied, whatever may be the case, object rolling on a plane surface or the object rolling on the inclined plane. In any of the case, the line joining point of contact till the center, this line must be perpendicular to the plane in which the object is rolling, and this is not happening. And that is why I differ from this argument. The maximum value of theta for which this football should roll should be given by this condition. So I disagree to it. As we rotate plank XY further, a situation arrives when this football starts rotating about this point of contact B. When it rotates about point of contact B, then in a particular situation, at a particular moment, this line BO becomes perpendicular to the plank XY. So this will be the moment when this football will begin to roll. So the condition that the football begins to roll is that the BO should become at least perpendicular to XY. This is the primary requirement for the rolling. Next, let's assume at this particular moment the plane of the circle subtends, makes angle alpha with the plank, and if this is angle alpha, then the angle made by the plane with BO will be 90 minus alpha, and angle COB will be equals to alpha. Angle COB is equals to alpha. Further, I mean, simple argument will also suggest that as weight W is always vertically downward, and hence this angle BOW is will always be equals to alpha, and the simple argument will also suggest that at this particular moment when this football is about to roll, and the angle made by the plank with the horizontal is alpha. Now in triangle COB, sine of alpha equals to CB by OB, and this is equals to small r by r. So the answer to this question is still small r by r. This angle sine alpha is equals to small r by r still matches with one of the option. But you see, my argument is different than the argument presented by the different masters in the field. So I mean, this should give you the enough idea under what condition this football will start rolling down, and what is the figure like the instant the football rolls. Now I want to leave you with one or two arguments. The first argument wanted to ask from you is that, now assume there is no friction between the football at different point of contacts. Now as the plank is rotated, what should happen to the football? Will it remain stationary, or will it rotate clockwise or anti-clockwise? This happens to be the first question. And the second question I'm leaving with you is, now as the plank rotates, what will be effect? What will be at what points the normal reaction will be more, and in fact at which point normal reaction will be maximum? You also need to tell me the point when the normal reaction at this point A becomes 0. Dear friends, let's discuss question number 2. In this question, we have a light disk made of aluminium. Aluminium happens to be a non-magnetic material. It is kept horizontally and is free to rotate about its axis as shown in the figure. So here is the figure. This aluminium disk has some thickness, and this aluminium disk is free to rotate about its own axis. A strong magnet is held vertically at a point above the disk and away from the axis. As you can see over here, here is a strong magnet. It has been kept vertically over this disk and is slightly displaced and is slightly away from the axis of rotation. On revolving the magnet about the axis of the disk will rotate in the direction opposite to the direction of magnet rotation, rotate in the same direction as the direction of magnet's motion. The disk will not rotate and its temperature will remain unchanged. Will not rotate, but the temperature will slowly rise. So these are the four different options. Now let us try to visualize this in a top view. This happens to be the side view. The top view, it should look like this. Here is a disk of radius capital R. This point, axis is passing through this point, through the center of this disk, and is coming normally outside. And a magnet is placed at distance R from the axis. So the magnetic field lines, they're entering into the disk. Now they not only enter into the disk, but if you draw the magnetic field lines, then you will notice these magnetic field lines, they also has to come out. So the magnetic field lines are not only entering, they're entering through a small cross section. So this is the cross section through which magnetic field lines are entering. I have shown these by crosses. So magnetic field lines enters through this small cross section, but magnetic field lines, they come out from elsewhere. From all these points, magnetic fields are coming normally out of the page. Is it right? The strength of magnetic field at all these points will be different. Anyway, now let's see. This magnet, let's assume this magnet is rotated in anti-clockwise sense. Now as this magnet is rotated in anti-clockwise sense, now let's assume the magnet rotates by d theta in time dt. So this is the angle by which the magnet has rotated, d theta. Now as magnet rotates, let's see that what happens. So this was the region through which magnetic field lines were entering. Is that right? Now as magnet is rotated, what will happen? The magnetic field lines through this region will decrease. So magnetic flux through this region should decrease, but at the same time magnetic flux should increase as the magnet is rotated. Is that right? So in one segment magnetic flux is decreasing, and in the other segment magnetic flux should increase. Now because there is change in flux in both the regions, and hence the EMF will be induced. Now induced EMF, you see, this is written as minus E dot dl. Is that right? So the induced EMF ensures that there should be production of electric field. This electric field is non-conservative in its nature, and non-conservative electric field, I mean this is always in circular form. Is it okay? So non-conservative electric field is induced within this metal. So because of the production of the electric field, the electrons within this segment, not only in this segment but also in this segment, the electrons, they will experience force, and the electrons experiences force, and hence the disk will experience force and disk will move. Now let us try to find out the direction in which the electric field is, the direction in which the electrons will experience force. Let's use the Lenz's law. So according to the Lenz's law, you see this is the region in which magnetic flux will decrease, yes or no? So the induced EMF will be, the sense of induced EMF should be such that it opposes the very cause which has produced it. And similarly, this is the region in which magnetic flux is decreasing. So as per Lenz's law, I mean the direction of induced EMF or the direction of induced current within this region should be such that it opposes the very cause that has produced it. So see, because of the production of the electric field, there will be electron movement. Because there is electron movement, so current is also induced. Is it right? And the current induced, let's assume induced current is like this, and we will see that why I have chosen the induced current like this. Now if we take induced current like this, so because of this induced current, magnetic field within this region should be downwards, and on the other side magnetic field will be coming normally upwards. Is it okay? So you see, as the magnet is moved, what is happening within this region? Magnetic flux is decreasing. If the direction of current happens to be radially outward, as I have chosen, then the magnetic field produced by this current will try to oppose decrease in magnetic field. Is it right? And over here, the magnetic flux within this region, it was increasing, and so produced magnetic field. By this induced current will try to oppose any increment in current. So the direction of induced current, I have chosen that to be correct. Is that right? So this should be the direction of induced current, which is roughly in the radial direction. Now let's see, because the electric field, because the current is radially outwards, so current is radially outward, what really it means is the electron should be moving in the inward direction. Now as the electrons in the whole segment, let I draw this separately for you. This is the direction in which current is increasing, and all the electrons, they have the thermal velocity, and the average thermal velocity is 0, so I am not bothered about the thermal velocity, but so I will take care of the collective motion of the electron, which is got to be inwards. Is it right? So effectively all the free electrons within this metal, they will be moving in this direction because the current is radially outward, so free electron, they got to move radially inwards. Now apply Fleming's left hand rule. Now as we apply Fleming's left hand rule, direction of the forefinger represent direction of magnetic field, which is normally inside, and the electrons, they are moving in this direction. Then thumb represents, you see, thumb represent direction of magnetic force provided charged particle moves in a direction represented by the middle finger. So the electrons, these electrons will experience force in a direction opposite to the direction shown by the thumb. So all the free electrons, they will experience force like this. And this, because of the collective force, the whole rod, the whole disc, in fact, the whole disc has to move in the direction magnet has been moved. So we understand that the disc should rotate in a direction in which the magnet has been rotated. That's fairly fine. Now let's see the other things, other options given. Will rotate in a direction opposite to direction of magnetic field. This is false. rotate in the same direction as the direction of magnetic field. This is a correct statement. Now will not rotate, these options, I mean, got to be totally incorrect. But definitely we should look for whether temperature will increase or will not increase. I'm telling you the temperature will increase. Why the temperature should increase? And the reason is obvious, that this electric field happens to be non-conservative in nature. This must constitute a circular loop, and hence the electrons, they got to move. They got to move in a circular loop, and the current should also be in the circular loop, which I can discuss at some other time. And hence, because the current is flowing, and hence there should be Joule's heating effect, and hence this aluminum disc should get heated up slowly. So if you want more and more analysis of different physics topics, you should subscribe my channel to get notification in time. And thank you so very much. God bless you.